monitoraat is possible as well, but if now what is done, go ahead, Tristan. Yeah, go ahead. Which one? I need to look it up as well. What about 19? Exercise 19. It's the last ones, the new ones, I guess. I don't know, monitoraat, that's cool, huh? Antoine? No, it's at school. Of course, in real life, please. It's much easier to talk and you have no risk of it falling out and things not working and whatever. Okay, 19. Beam directly on the beam. Okay, if you look into the movie that I post the link, Tristan, on the movie, it shows a nice example at the end. So if you have a moment directly applied to a beam, you don't have to take it in consideration with the shear forces. It's not a shear force. So you just do as it's not present for the shear forces. But then, of course, it's like a sudden drop or heightening, depending on what is applicable to, positive over negative, in your curve of bending moments. Only for the bending moments, it has an effect. Yeah, it's a direct bending moment, only bending moment. It has no result on the shear forces, and it gives you an immediate drop on the spot where it's positioned, of course, when you draw your diagram, positive or negative in your bending moment curve. Okay? Very nice, you got there at the end. Perfect. Some others who have questions? So far, so good? Okay, so this will be the last online contact moment with me. The next one will be the monitoraat, as we have posted on Blackboard. It will be the week after, I think in 2 weeks, because next week you have course in school of Professor Hage, which you are familiar to, of Ship Construction 1. Yeah, and he will normally teach you then that day onwards. Okay, then we discussed question 1, exercises, which is a beam of which you need to calculate shear force bending moment at certain positions, and you need to draw the shear force bending moment diagrams. Exercise 2 will be a vessel-like shape, box type shape, with a certain cargo distribution. You need to calculate shear force bending moments and draw the diagrams. And then we come now up to part 3 and question number 3. And question number 3 will be you need to relate your shear force bending moments to tensions. Because, of course, the story is that you're not allowed to cross within your structure the yield point, taking into account, of course, in practice, in reality, a certain kind of a safety margin. Yeah, but that's in way the restriction are stresses, practically speaking, rather than shear forces and bending moments. Although I know on board of a vessel you only see diagrams, shear forces, bending moments, but the knowledge behind, which it makes it an academic touch to the entire course, is that you need to be able to relate it to really the basis, meaning the stresses involved. Let me see where we ended up with the presentation. So I first have to, yes, what you see in the presentation that I skipped, but you need to know that the exercise we did last week, yeah, they are simple approaches that we did. The simply shaped whole box type is a simple approach. Of course, it's not realistic, because in reality, your distribution of Archimedes, your upward force is, of course, not uniformly distributed evenly over the entire length, over the entire length of the beam. which we took into consideration. The same is valid with the light ship. The light ship we took as uniformly distributed over the entire length of the beam, which of course is not the case in reality. Yeah. In reality, you also have to take into account the wave actions, which result into bending moments, and that we did not do. So the dynamic part was not taken into account as well. Yeah. Also, if you have a trim or a list, then you will have also different moments. Your distribution will be different. So you have to, the buoyancy port side, starboard side is not exactly the same if you have a kind of a leverage to port or to starboard. And this is not taken into account as well. So we do only simple approaches, just that you get the idea behind it. And that's, of course, the basics. What else do you see in here? Is that you see you're not allowed to cross the limits, end of the line. So it's a responsibility for you because it's well calculated, well reasoned by the architect, the naval architect. He gives you boundaries, restrictions you're just not allowed to cross. Yeah. But you might say that, okay, when we are in port, yeah, those boundaries of shear force and bending moments, why do they have to be that high? Because in port you're nice sheltered and are not exposed to so much exterior forces, because when you're in a sheltered location, for instance, it's different than when you're a tanker on a T-bird. But presume that you are a container vessel in well protected berth, yeah, then you are less subtle to all those wave impacts and those wind impacts. So it will limit, of course, the stresses in your structure. So why can't we cross a bit those limits then in port? This is mostly applicable to bulk carriers, and you will see for sure for bulk carriers, if you might go navigating in the future, that you will get two sets of limits. You get one set of limits, which is the most stringent, of course, for when you're navigating at open sea, because then you're exposed to the worst case conditions that evoke stresses on your structure. But if you are in harbor, you're allowed to go a little bit higher. But my advice, and the advice I have to give to you, is try not to use that second limit when you're in harbor. Always try to use the most stringent one, and only if it's not possibly otherwise during loading and discharging, you might have some flexibility and you might have a little game room playing with shear forces and bending moments. Yeah. Because in port you have less exterior forces that lead to stresses, and that might be incorporated by the naval architect, and it might give you two limits. Yeah. The limits given by naval architects are always explained as being still water bending moments. Why? Because in your calculations on board, you're not taking the dynamic part into consideration. It's already subtracted. So all forces which your vessel is exposed to is, of course, the static ones, which we calculated so far. But next to that, you also have the dynamic part of the wave and the winds. But this the naval architect already takes into account, and he gives you limits that only considers that static part. And that's why it's always mentioned still water. Yeah. But no, in port, you might have two sets of limits available for sure for bulk carriers. That gives you a little of a room to play with in case you're discharging and charging in port, because it's not always that easy for sure for bulk carriers to stay within the stringent limits of the seagoing limitations. Yeah. So that was what I still want to tell to you when it comes up to the calculations we did last week. But what will we do this week? We will try to link those shear force and bending moments to stresses. Yeah. Now, okay, you have those, what is modulus of elasticity, stress over strain, and those things. You know that stress is force divided by area. That is knowledge you need to have from ship construction 1. Yeah. But if we go straight to a vessel is not like we had in ship construction 1, like a kind of a small piece of metal that you expose to attraction, and then see what's going to happen and see that you're not crossing. So and then if you calculate then the stresses as we did in ship construction 1, it's force divided by area. If you remember somewhere in the back of your head. Yeah, that's a simple cross section of one simple plate which is exposed to a certain force. Now we have a full construction, an entire construction exposed to forces that lead to stresses, which is a puzzle of plates. Yeah. Now, how do we express the resistance against bending, the resistance against all those exterior forces and bending moments of the entire structure is expressed by a moment of inertia. Yeah, the area moment of inertia. And that you should be able to know how to calculate it. It gives you a degree of resistance against bending. Yeah. Uh, Suppose you want to calculate your area moment of inertia of just a beam, a solid beam type with a certain basis and height, as expressed here, then you see appearing a formula that you all should know from the course integral calculation of the first bachelor. Yeah, and it's the basis multiplied by the height to the third divided by the 12th. Yeah. Now, of course, it depends on how you formulate the basis and how you formulate the height. Yeah, and we always look at to a vessel like it's upright, and the basis is sea level, the height is up in the air. Huh? And if you look like here, for existence, a man walking upon a beam, depending on how he walks upon the beam, how your beam is positioned, vertical or horizontal, you have a different resistance against bending. Yeah, you also have a different moment of inertia. Yeah. And then I think that you might have some calculations that I gave you. Let me see, because I do not have the Word document with me, that I ask you to make a calculation and to compare both of them. Yeah, but that, okay, it's just filling in the formula, basis minus height to the third divided by 12. Let me have a look here into my what I gave to you. Yeah, it's exercise number 8, I guess. If you go into the course, it's this one. There it is. It's on top. I was a bit too fast. Yeah. So if you go to exercise number 8, yeah, and you see the comparison between both, visually you compare it as somebody walking on a beam. Yeah. And then you can calculate the resistance against bending by calculating its area moment of inertia. Yeah, area moment of inertia, basis multiplied by the height to the third divided by 12. And then you will see that the one from the first version will be a lot higher than this one, which is normal because the height is tremendously bigger than the one on the right hand side, and that is taken to the third, of course, is predominantly present. Yeah. And then what do you see? My question to you, yeah, if you would compare this one beam or the other beam, resistance against bending, yeah, to stresses, more or less stresses, how would you, I will take it later on, stress level, because then I'm going to mix up too much at one time and then it might get confusing. Yeah. But if you see here, let's go straight here first. You have your beam type. How were the stresses developed throughout the cross section? Yeah. Then we told last year that you can compare a vessel's hull with an eye-profiled beam if you want to make a comparison with a simple beam type. Yeah. And then I explained to you that the development of compression tension develops like this. Yeah. So you have at a neutral axis where you're exposed to bending, you have zero tension or compression. And then when you go further away from the neutral axis, you go to the highest part of the compression and tension. Yeah. So if your vessel here is exposed to sagging, yeah, the bottom flange of your eye profile beam will be submitted to tension. The upper flange will be submitted to compression. Yeah. So you have here compression, you have here, you have tension. And if you have a lot of resistance against bending, then your I is big or small. Is your moment of inertia big or small when you have a lot of resistance against bending? Is indeed very big. Yeah, so try to visualize this one. So you have a lot of resistance against bending. Yeah, what will be the stress level? Stress level of compression and tension. What do you think just on your idea? Will they be smaller? If you see those two beam times, let me put it differently. Yeah, and you compare the evolution of compressive stresses and tensile stresses over the height of these beams. Yeah, where will the stresses be the biggest? In the first one or the last one? The biggest is the right one, of course. But your I, your resistance against bending is smaller. Yeah, no, I have to draw it differently. Wait 1 second, because it's smaller. Yeah, so you have your area moment of inertia here is bigger, much bigger than that one. Yeah. If you look at the stress levels, on the other hand, yeah, let me put it this way with bases and tops. Yeah, then indeed here the stress levels will be much more taller than here, which results in what? So if you say that your stresses is here smaller, but I is bigger, this here stress levels is bigger, and here I is smaller, you can say it is inversely proportional to one another. So it gives you already something to think about. So later on, we will try to formulate if something is subjected to bending like this. It depends on a certain aspect. It depends on what is the shape of your vessel, of your vessel in this the beam. What is its resistance against bending? Because there's a link between both of them. So there's a link between stresses and I. And as you can see, it's inversely proportional. So somewhere soon in your formula, you will have an I below, because if I is big, tensions are small and vice versa. Yeah. What else might be a predominant factor in your stress level if something is subjected to bending? Bending leads to compression and tension. What is another factor do you think that might be important? Two things. One that you know from ship construction 1 is the material. Yes, of course, the material in a way, but the material in a way is also expressed by its shape through the area. The material, how can you calculate it as well? The bending moment itself, the force you expose to your beam. Yeah. So if you put somebody on top or not, if you don't put somebody on top, you do not have stresses. If you put somebody on top, you do have stresses. So the external forces, yeah, are also important. When we talk about bending, we talk about bending moments. We're gonna separate bending and shear from each other. Yeah, in reality, they're combined, of course, but if we do calculations, we separate both of them. So the bending moment that takes place here will define in a way the stresses. The bending moments that take place, I'm still not able to here or here or here, is depending on the local internal bending moments. The reaction forces due to the external one, they're linked to one another. So if you have the external one, you can calculate the internal one. So your stress level will be dependent on what? The bending moment exposed to at that certain spot. And you know you have bending moment curves. Yeah, might have a bending moment curve like this over the entire length. Means that you have stress levels which differ depending on the place that you will calculate it, because you have different bending moments on every spot. And it is also depending on what? It's also depending on the distance from the neutral axis. So if you are close or on the neutral axis, your stress level is 0. But if you go further away from the neutral axis, you heighten your stress level. So this distance from the neutral axis, which we call y, is also a factor determining your stress level. And there you have your formula. And this is the formula that links bending moment to stresses. So it depends on the bending moment at the spot where you want to know your stress level. It depends at what position from the neutral axis you want the stress level. And it depends on the resistance against bending from the structure. And then you get your stress level. And that is behind the shear force and bending moments. In this case, bending moments, shear force will be similar, that we have restrictions. And this one, in order not to fail, should be lower than your yield stress, taken into account, yes or no, a safety factor of safety margin. And that's the whole idea behind. Yeah. Okay, now the question is, a ship structure is composed out of more than one plate. How do you calculate the resistance against bending for a composed structure? For more than just one simple beam, because for one simple beam, it's easy. That's we did like this. But a vessel is not just one simple beam. Yeah. So we need to know the cross section is different. Yeah. So far, so good or not yet? Okay. That's not clear then. If it's so far, so good. Like, let me take, for instance, a beam from previous talks. This, for instance. Yeah, we have here a point load in the middle of a beam results in a certain bending moment diagram. Yeah, that was the first calculations. I hope you still know a bit what this is, a bending moment diagram of a simple beam. Yeah, so it gives you bending moment values internally at different positions along the beam. Yeah, you can give restrictions to bending moments, and that's what the naval architecture does when you compare a beam to a vessel. But what's behind those bending moments lead to stresses. And those stress levels should not be higher than certain limits, because the calculation is a bit more difficult than just calculating the bending moment, than calculating bending moments easier than calculating stresses. Naval architectures make your life easy. Yeah? So suppose now your beam has the shape here of this B, H, a certain breadth and a certain height. And that is a profile of your beam. Your beam who has this bending moment exposed to. Yeah? What are the stresses in those beams? Okay, just take one spot now. We'll take the middle of the beam. In the middle of the beam, we have the highest bending moment in this case, equals 5. Obviously, that's 5 meters. The bending moment is equal how much? Who calculated it? How do you quickly calculate this bending moment? Who can do it for me? What is the bending moment in the mid-length of your beam? When the length of your beam is 10 meters apparently, and your mid-length is 5 meters, what is your bending moment? How many kilonewton meter? 50. Thank you, Tristan. Indeed. Why 50? Because if you are positioned mid-length of your beam here, you take this force into consideration, multiplied by the arm exactly, so it leads you to 50 kilonewton meter. That's your bending moment. Yeah? But here, the neutral axis is perfectly in the middle of your beam. Because if you take the area center of gravity, it's in the middle. Here. Yeah? Where do you have the highest stresses when it's subjected to bending? So it goes like this. it's sagging, yeah, then your stress level will be like this. Compressive, tensile, equally divided over positive, negative, because it's fully symmetrically. And you have the highest stresses the further away from your neutral axis. So at a distance y. So what are here? A stress level, the furthest away from your, to put a value on this here at this figure. How do you solve this? What are the stresses at the location the furthest away from your neutral axis at this location here? Yeah, equals what? The resistance against bending we put downwards, and we put the bending moment at that spot, what you calculated here. And then you can calculate the value exactly of that stress level. Yeah, and the bending moment you calculate at 50 kilonewton per meter. Y depends on the height of your beam. It's height divided by 2. Y is the height, in this case, divided by 2, because it's all perfectly symmetrically. And I is B h to the third divided by 12. And then you can calculate that stress level. And that stress level should be lower than your yield point. And that's it. That's the basic idea of today. And this is what for the bending moments. Yeah, explanation. Now let me head back to the problem that I wanted to stipulate. Because so far so good, we only have indeed just one beam, solid beam. Then calculating the resistance against bending is easy. But a vessel is composed out of a multiple game of plates. How do you then calculate the resistance against bending? Well, there's a little formula, and that calls the parallel axis theorem. And in a way, this is the only one you need to memorize a bit, because all the rest you already know. And if you practice, you know. So if you have, for instance, a shape of a structure like this, which is exposed to forces that lead to bending moments, yeah, and you want to calculate, you need to know from this structure what is its resistance against bending. Again, it goes like this in reality. It's in its length, and that length is exposed to certain kind of external forces that lead to internal shear force and internal bending moments. Yeah, the resistance of this structure against bending, yeah, is calculated. How? By considering the individual moments of inertia of each element separately. So, which is easy because these are all plates. It is indeed the basis multiplied by the height to the third divided by 12 for element 1, element 2, and element 3. All those elements need to be corrected with a correction towards the neutral axis, because we take the moment of inertia around the neutral axis to calculate the resistance against bending. Yeah, because why around the neutral axis? Because we know that around the neutral axis, your stress evolution goes, and it's 0 at the neutral axis. Yeah, suppose it's perfectly symmetrically, it will be mid-height only when it's perfectly symmetrically in area and volume distribution. It will be perfectly in the middle. What is that correction for each segment? It's the respective area multiplied by the distance towards the neutral axis. So here you see that it's individual neutral axis towards the integral neutral axis of the entire structure. That's the DI. And that you need to do for each element. When it's perfectly symmetrically, of course, this correction factor will be equal to 0 as the distance is equal to 0. Yeah, and you only have to take into account the top and the bottom flange only when it's perfectly symmetrically. And you sum them all up. You just make a sum of all. And that is your resistance against bending, area moment of inertia, of the entire structure, which in this case is an I-profile beam. Yeah. To put it in a bit more practical with figures, you have exercise number 9. And exercise number 9 gives you here an eye profile beam. Yeah. And for that eye profile beam, you need to make a calculation for the Y, area moment of inertia, but they ask you, they neglect now in this question neutral axis. They just tell you we need to know why the resistance against bending if bending takes place around the line X here, this line. Know that in the future, when you look at two vessels, we really need to know and calculate the I around the neutral axis. Yeah. But it's just an example how to calculate through the parallel axis theorem. Yeah. So if you then go to the calculations, that I think you will find in the Word document as well, you have every segment individually. You need to know the Y. So of element A, B, and C, you need to calculate, and you need to correct them. You need to correct them towards the reference line where you do your calculations for. Yeah, which is the surface multiplied by the distance squared. Here, the distance is 0 because you are on the spot and it appears to be in the middle of your web. And then, of course, this correction is 0. And you just sum it all up. And if you sum it all up, you end up with the resistance against bending in case your bending takes place around this axis X. Yeah. Now, so far, I already another example. No, we go straight here. So the position of your neutral axis is not always given. Yeah. For sure, when I give you a cross-section of a vessel or the cross-section of an eye profile beam, I give you the dimensions. But I'm not telling you where the neutral axis is positioned. Like, for instance, here. Yeah. Here it is given, or in a way, yeah, okay. For instance, here, the dimensions that I give is what? The dimensions of your upper flange, the lower flange, and I give you the dimensions of the web, meaning the breadth, the height, the breadth, height, or thickness, if you like, the thickness of the plates and the width of the plates. Yeah, or the height of the plates, respectively, what you're talking about. Yeah? But it's not giving you the exact position of the mass centroid or the centroid of these surfaces, which is a bit the same way, the same thing. The centroid or position of gravity, center of gravity, if you like, of the area or of the mass of your entire beam. Where is it positioned? It's not given. That you need to calculate, because in your calculations later on, you need to know the moment of inertia around the neutral axis. And this should be your neutral axis. So you need to be able to calculate that. So how to approach and how to calculate the neutral axis. Then you will see in your course handouts this example, exercise number 10. Yeah. Exercise number 10 asks you two questions, if I'm correctly. Yeah. The first question of exercise number 10, help me out, because do I have it at hand? The Word document, yes, luckily I do. I only have here. The question is, if you go to the Word document, two questions. The first question of exercise number 10 is calculate the moment of inertia around the x-axis. So it means around this horizontal one. How do you calculate the moment of inertia around this one? Okay, this is easy. It's just a parallel axis theorem, which means that we need to calculate, if you take this as element 1, you take this here below as element 2, you take this here below as element 3. Yeah. How do you calculate it? Your y around x equals the I of element 1 plus, where do we have find plus, the moment of inertia of element 2 individually plus the moment of inertia of element 3 individually, plus each element has to be corrected. You corrected it by what? The area of element 1 multiplied by what? The distance from its center towards the axis where you want to calculate your resistance around. Yeah. So in this case, it means this distance. This will be D1. D1. Yeah. So if I continue, it will be a little more upwards. It will be D1, but squared. Let me put it like this for now. I guess you know what I mean then. If he wants to. No. Yes, squared. And I close plus correction 2, area 2 multiplied by distance 2 to the squared squared plus area 3. I'll explain later. I first type it all out. Distance 3 to the squared. There you go. So what is a parallel axis theorem? The resistance of the material against bending. In this case, moment of inertia that we calculate around X is of every segment E individually, and every segment has to be corrected towards this line where you calculate the resistance around. Yeah, it's the surface of the respective areas by the distance here squared. For your second one, this will be the distance squared. For your third element, this will be the distance squared. And then you have your I. Yeah. This is one thing, but this is not applicable if you want to calculate the stresses. You need the Y around the neutral axis. Now, where is this located? That's a question mark. How do you calculate its location of C? Yeah. Actually, it's not that difficult. Yeah. Calculating that distance, this distance Y, you do by multiplying the areas of the segments by a distance of your choice. Me, I usually take as reference the basis of the entire profile. You do whatever you like. You can take mid height, you can take the upper part. With me, I find it easy to always take as a reference the distance from every segment towards the baseline. So what do I take? I take the distance from here to the baseline. The distance from here to the baseline, from that segment towards the baseline, and this is my Y. Okay? But here the numbering of the elements is not the same as I used in the before. Right? So you see 5 by 1. 5 by 1 is clearly this as element 1. And for as element 1, you have 0.5 as a distance towards X. Yeah. Element 2 is 1 or the 2 beams, either left or right, as if you like. They're exactly the same in dimensions. So you have here exactly the same dimensions. The distance towards X is exactly the same. So you have exactly the same value in distance. This you sum up. And if you sum this all up and you divide it by the total area, you end up with the distance, because you have an area multiplied by distance divided by the total area, again an area, you end up with the distance, and that is the position of your center point. And that you need to take as a reference for your calculations of Y around the neutral axis. Yeah. So if I then draw the line here, if you calculated this position here, you can calculate E around the neutral axis if you have that location without any problem. Yeah. How do you calculate that? I gave you an example here. Yeah. This is how I do it. So I put it in an Excel sheet. It's easier for me to make exams and questions. And you can use Excel sheets or you can just write it out in one single line. Okay, let me write it out first in one single line to explain it to you. Yeah. So the I around the neutral axis equals what? The I of element number 1. Element number 1, which in this case is then, let me keep the same notations as here below, plus a correction. What is the correction? The surface of that element, the area of element 1 multiplied by the distance towards the neutral axis from that element centroid, squared, which means, which is this distance, because here you have it centered towards there. You just calculated y, which is 2.5 centimeters. Half thickness of this element is 0.5. So it leaves us up to what? 2 centimeters. So this distance is 2 centimeters. And that you do for every element. So you do plus moment of inertia of element 2. You correct that element 2 towards the neutral axis. The same you do for element 3. And you correct element 3 towards the neutral axis. And then you have your moment of inertia around the neutral axis, which gives you an exact resistance against bending of a profile that we can implement later on into a formula to come up to the stresses. Yeah, and that's the idea. So this you will need. So you will get like perhaps a distribution, and you get a cross section, and you need to calculate the moment of inertia. Of course, it will be step 1. If not, you're not able to end up to come with stresses. So it will be part of an exercise, part of your third exercise, this one. Yeah. And then you have multiple exercises within the course. So for this, you need to calculate the position of your neutral axis. Are you able to do this? Calculate the position of the neutral axis of this I-profiled or I-shaped beam? It's not necessarily the middle, because it's not symmetrically. Yeah? Your area center of gravity depends on how the material is distributed. You see here, if you go into your reference line of your neutral axis, the amount of area below is exactly the same as the amount of area above, but it's not necessarily mid-height of your profile. Yeah. If your profile is 100% symmetrically, then of course it will be exactly in the middle, mid-height. But here you see you have much more material below than you have material above. So your neutral axis will be positioned a bit more to downwards. Yeah. And this is comparable as well with a vessel. A vessel's neutral axis is always positioned a bit lower. Why? Because you have your double bottom. Your double bottom, which is similar to this one, your lower flange. There's much more material in the double bottom than in your upper or your weather deck. And that's why your neutral axis of a ship is always a bit lower than mid-height. Meaning that if soon you would like to calculate the maximum stress levels at a certain position along your beam, when you have calculated how your bending moments evolve, yeah, and you want to calculate your stress level. Suppose you have calculated your bending moments on that spot. Suppose you calculated the resistance against bending by calculating your moment of inertia around the neutral axis. Yeah. What distance do you have to take into account to, at that certain spot, at that certain cross section, to come to the maximum level of stresses? What will be the distance you have to take into account? Assuming that this is the distance you used to calculate the position of your neutral axis. What will be the y? The further away you are from the neutral axis, the higher your stress level. So if you go back to ship construction 1, you see that the evolution of your stress level is like this, huh? So it goes up, 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 up. So you have much higher stress level here than you have in the bottom, huh? And that you saw in ship construction 1. And that is why, if you do not recall these talkings, please revise ship construction 1 because it's all linked to one another. Yeah, the higher, the further you away from the neutral axis, the bigger your stresses are. And as your neutral axis is lower than mid height of your profile in general of a vessel, then the distance you have to take into account to come to the worst case stresses on that spot will be, of course, this end, huh? This part. And that is much bigger. So this y is bigger than yx. So you always have to check where is your neutral axis located. A bit more downwards, a bit more upwards, perhaps perfectly in the middle, then you know compression tension is nicely distributed. But when it's a bit more downwards, like most of the time it will be because I will make exercises similar to vessels, as you have in reality, then you will see that your maximum stress level will be higher at your upper deck and lesser in your double bottom. Yeah, and that are links connecting ship construction 1 to ship construction 2. Yeah. What you will see then in the course, of course, is this formula. The formula that I explained to you. Suppose that this is your vessel exposed to bending. You have bending moments over the entire length of your beam. Now, in this case, suppose your bending moment curve of your vessel goes like this. Suppose. You have a maximum in the middle. Yeah? Maximum worst case scenarios, you want to make sure that it's fine to know if your beam or your vessel will yes or no fail. Yeah? So suppose that you want to know here what the tensions are. This will be the most point of interest because there you have your maximum bending moments. When your bending moments are very big, your moment is big, it's proportional to your stresses, means your stresses are big. So you take worst case scenario where your bending moment is max to see whether yes or no you comply with staying below your yield point. Yeah? What else do you need in this formula? The moment, of course, maximum moment, worst case scenario, resistance against bending. Why? Of course, because it's 100% linked to your stress level, depending on the shape of our vessel. Not every vessel with a certain shape has the same resistance against bending, and that's incorporated in your moment of inertia. Yeah. Of course, you need to know where your neutral axis is located because you need to calculate this around the neutral axis to have a valid outcome. And then, of course, to know the worst case scenario, you need to take into account the furthest distance away from the neutral axis. So here, suppose you have indeed this cross section, like it's stipulated there. The distance from the neutral axis is the biggest from this point onwards towards your weather deck, if you like. So it will be this y you have to put into your formula. And then you get your maximum stresses that your vessel is exposed to at a certain point. Yeah? So max is bending moment max multiplied by y max divided by I. So if this is in order, then you can say that your beam is fine and will not fail. But as soon as that stress level is higher than your yield stress or the restriction given by naval architects, or naval architects use as a reference, usually it will be your yield point taking into account a safety margin, neglecting now a bit the safety margin, just taking as a reference your yield point. As soon as your maximum stress levels that you encountered on board are below the yield point, your structure is fine. Yeah, and that goes behind the shear force and the bending moments. But of course, now I'm only focused on the static part and not the dynamic part. Dynamically speaking, we make it more difficult, and that's not the point, because on board you only are restricted to the static things. That's the only thing you have at hand as a captain. You do not have the dynamic part at hand. That has a naval architect to calculate prior to constructing a vessel, of course. Yeah. But this is okay. This is a very simple illustration or representation of a vessel if you compare a vessel with an high profile beam. Yeah. You can also make your exercise a bit more realistic, like this, for instance. So what do you have? You have a shape of a vessel composed out of plates, upper deck, second deck, tank top, centerline girder in this case, and you have your side shells, all with certain dimensions. All the dimensions are given. Are you able to calculate now the stress levels in the upper deck, the stress levels in the second deck, the stress levels in the tank top and bottom shell? Yes, you're capable of doing so. What do you need to know? Of course, the bending moments. The bending moments are the calculations we did the past weeks. Suppose you have your bending moment given, and I will give you a bending moment as an assumption. What will be the evolution of your stress at a certain point? Suppose we are at a position where your bending moment is max. It's always nice to look at where your moments are the max, because it gives you the maximum stresses. You know, your stresses evolve like this. Up. You see your neutral axis, it is a bit lower than mid-height. Realistic to a vessel because you have more material in your bottom than in your upper deck. Yeah. What is your stress level? This is your stress level. How do you come up to that stress level? The bending moments multiplied by the respective distance divided by y of the entire structure, the resistance against bending of the entire structure around the neutral axis. That's what you need to calculate to find your maximum stresses at this point. Can you calculate stress level at second deck point? Of course. The only thing you need to adjust is what? From your formula. It's the distance. Bending moment max on this location stays the same, because if you look at your vessel like this in lengthwise, your bending moment at a certain spot is the same considered for this entire cross section, of course. What will be the factor that will vary your stress level? It will be the y. So you take your bending moment multiplied by this distance divided by the resistance against bending around the neutral axis, and you get your stress level for the second deck. The same you do for tank top and bottom shell. But then you take your distance as this and that. Yeah? And that's an exercise which I gave you in your Word document, which is totally worked out. So if you go to the Word document, this exercise is fully made for you. And you can just try, but my suggestion is try to make it first yourself. Close your Word document, make it yourself, and then go and verify and check afterwards, please. Yeah. And then you will see that the Excel sheet that I use will be a bit more elaborated because you have your more structural elements to take into consideration. So what do? The area multiplied by a distance versus a reference point. You sum it all up, you divide by the total area, and that will give you the distance from the neutral axis towards your reference point, which you take as you please. If you have the position of your neutral axis, you can calculate the moment of inertia of the entire profile, meaning the moment of inertia of every element individual. And we always talk about place, so it's easy. Its base is my height to the third divided by 12. Yeah. Very, very small one might be neglectable, but that you will see, you can take into account as well, but it will be very, 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 very small and not really of interest. Yeah. And then you take a correction. And what is the correction? The surface multiplied by the distance of the element towards the neutral axis. And then you sum it all up, and then you end up with the moment of inertia around the neutral axis. Yeah. And then to visualize what I already visualized before, you see here the stress levels at the point where your bending moment is given, or for the point that you calculate it, and you can calculate it for every level. You can make your calculations. Yeah. Now you tell me, yes, madam, okay, it's a nice story for bending moments. Well, what's up to shear forces? I don't know if you recall, but for shear forces, to the contrary of bending moments, then all the shear stresses, they're most of all concentrated here in the web. So what can you do? You can use, because I think you already have enough time will be necessary to calculate your compressive stresses and tensile stresses. Then to calculate your shear stresses coming from shear forces, you can use a approximation, meaning what? Shear stress, the word explains it in a way itself. Stress is equals to what? Force, shear force divided by what? Divided by, you know, from ship construction 1, stress is force divided by area. What area do you take into consideration now? The total area of your profile? Oh, that's too much of an approximation, because you know that in the upper and the lower flanges, there are nearly no shear stresses present. They're mostly concentrated here in the middle of your profile when we talk about I profile beam. When we talk about a vessel, it means your side shells and all longitudinal elements going straight up and forth your vessel. There, your shear stresses will be concentrated upon. So if you have problems with shear stresses on board, most of the time it will be your side shells. When you have problems with bending moments, most of the time it will be in your upper deck. It were questions upon the exam of ship construction 1. Yeah. So what area did you take into account? If you calculate the shear forces divided by area, what will be a representative area to come up to the stresses, your stress level? The area of the web. Only the web. If you make an approximation, you may have to make a good approximation. Huh? So you take the area of the web into account, because it's mostly located here in the web. It's distributed over the web, all the shear stresses. And that's a link again with ship construction 1. Yeah. And that's it. And that is a calculation you will be able to do. So revise mathematics, revise ship construction 1, and then go into the Word document. For those who are prepared, yeah, what I will do with you is make the additional exercises, which is new when compared to last year. I think it's exercise number 20, I guess, as Tristan asked 19. So I deduct that it should be then question 20. What do you see in your Word document for question 20? I did not print it out yet, but I think I know it by heart. I used 2A to come up to 2B, correct? You all find it in your handouts, or do you want me to put it here on the screen? You have your handouts with you? The Word document? Participants present, do you have the Word document with you or not? Yes. Okay, some of you do. Okay. So indeed, Tristan, thank you. 2021. Yeah. So I think it's question number 21, the last one. Yeah. Let Let me see if I have it here. I'm not sure. Otherwise, I have to upload it. But if you have it at hand, it's easier. Yeah. So question number 2a, it's with me, but with you, it must be 21 or 22. Let me take a whiteboard now. Yeah. You have a box type vessel with 7 holes. I think we made that exercise even last week. This one. Yeah. 1, 2, 3, 4, 5, 6, 7. Yeah. It has a certain cargo distribution in the uneven tanks. It's alternately loaded. Yeah. And I ask you to calculate the shear forces and the bending moments at every intersection of the tank. We did this exercise last week. Yeah. Then the question is, in the next question is based on this one, is consider that the midship section of your vessel is simplified, yeah, even keel hull, and it's indicated as having the profile side shells. You have a weather deck, you have a double bottom, and you have a centerline girder. That's it. And the dimensions are given. And then the question is, calculate the bending stress diagram at mid-length, meaning that you're located here in the middle of your vessel, mid-length at 70 meters. And I'm asking you for here, for this cross-section at that location, what is the stress diagram? How do these stresses evolve? Yeah. I'm not talking about shear stresses in this case. I only ask you to focus here on the bending stresses, not the shear stresses. Yeah. Compressive and tensile. That's the question. Huh? How do they evolve? You already know a bit how it will be. If you know somewhere you have a neutral axis, you know the neutral axis will be lower than mid-height because your double bottom is much more heavier than your weather deck. And you know that they will evolve like this somehow, somewhere. That is fixed. That's knowledge you have from last year. Yeah. Now, how do you come up to values? Because, of course, diagrams, they ask for values. First, you need to know what is the bending moment at 70 meters. Because your stress level here, which is the highest at your weather deck, as we explained, because this distance from your neutral axis will be the biggest, it is Y max. Yeah. You have to multiply by the bending moment and divide by your resistance against bending to come up with your stresses. So this stress level here equals bending moment max at 70 meters multiplied by Y max divided by the resistance against bending, your moment of inertia. So this we all have to fill in to be able to calculate that value at the weather deck level. If you have your bending moment, if you have your I, you can easily calculate it as well for your double bottom structure, meaning your lower plate as well as your tank top. You just have to vary wide the distance and then you have your values. Yeah. Bending moment max we calculated last week and it was given as 52,500 ton meter. Where your bending moment is maximum, your shear force equals to 0. Yeah, so your shear forces at that spot, of course, are equal to 0. And your bending moment was equal to, at 70 meters, 52,500 ton meter. That you recall from last week? I guess so, huh? Now is a question. Okay, we have the bending moment. We calculated it last week. Why we need the I we need. So first question rises, what is the position of our neutral axis? Because we need to calculate I, our resistance against bending around the neutral axis, and we need the distance from the neutral axis. So where is it located? Question mark. How do you calculate it? With the parallel axis theorem, as I told you before. Yeah. So I'll take a new slide. You can make a nice tabular in Excel, as I do. It's very easy. But just now, as a reference, I will just do the opposite thing. Huh? And I will, because you will not have Excel upon the examination. Yeah. I will show you how to calculate it by hand. And then you have your side shells going from up, down, these dimensions. Yeah, so far so good. I told you we need a reference line. As a reference, I always take the basis of my profile. You do with it as you please. I do not care. You get it up, mid, low. It will all give the same result. I find it easy. Always take the same, just the basis of my profile. Hmm? Where is my neutral axis located? What is this distance? That is now the questions we have to solve. Yeah. It equals what? It equals the summation of all the areas multiplied by their distances towards x. Let me put here yx. Of all the elements present, if you sum them all up and you divide it by the sum of all the areas, you get yc. That's the formula you need to apply. Yeah. So far, so good. We'll be able to calculate this or not at home. It's just multiplying a cross section of every segment element individually multiplied by a distance towards x divided by the total sum of all the areas. Yeah, it gives you the distance yc. So far, so good. Yes or no? Yes, thank you, Freek. I can't see your faces, huh? So it's difficult. So it's good that we see each other in 2 weeks with the monitorat. Yeah, probably. Okay. So I think I gave you the solution somewhere in the course, and it will be an amount of millimeters, of course. Huh? So that's why you find this one. Now, the next question is, how do we find y? The resistance against bending around the neutral axis. What page can you find this, Bavel? Word document. You have 2 documents. Okay, there you go. Antoine is helping you out. There you have the question and the solutions. 26, there you go. And the solutions will be at the back. Okay. How do you find E around the neutral axis? You need to find first the y's of every segment individually. So of segment 1, segment 2, segment 3, segment 4, 5, and 6. You have to calculate its I. Do not forget, if you calculate it, its basis multiplied by the height to the third divided by 12. The height is in that direction. Huh? Do not mix breadths and heights, please, because then your calculation will be wrong. Breadth is horizontally, height is upwards. Okay, so breadth multiplied by height to the third divided by 12. But that's for every segment individually. We still have to correct it towards the neutral axis. The correction is what? The correction is the surface of the element multiplied by its distance towards the neutral axis squared. Yeah? This is a plus. And this you do for every element. And then you find the y neutral axis. But there are things you have to do. Okay, upon the monitorat, if you do not succeed, I can come and have a look at your calculations and see how you do it. But you have to, try to do things yourself at home in this case. Exercises, I can stand here and wait, but you have to make them yourself at home. What I propose, we still have some time left. There's only one exercise like this of this one, yes, but you have more in the course itself. If you go to exercise numbers that I skipped, yeah, you have some more in the beginning. So the course is built up as all the chapters with some sample exercises, and then you have additional exercises. Yeah, and those additional exercises by every year the list becomes bigger and bigger and bigger and bigger, and always add on to. And the further we are, the more exercises you have to make. So you do not have to make all the exercise. As soon as you understand the philosophy, it's always the same thing to apply. Yeah. But I propose sometimes I add the exercise of the examinations. Yes, indeed. Correct. Yeah. You can send mails as well, but we arrange the monitorat. I will be in school, so please take the advantage to make use of the monitorat as well. For sure, with exercises, it talks much easier. So I have a proposition for you now. Yeah? I'll stick here online and you make this exercise and see if you end up with the same results as you find out in the Word document. So try to find the position of the neutral axis of this exercise. Try to find the moment of inertia around its neutral axis and see if you end up with the correct result. Okay? Try to do it, and I'm still here in case you have questions. If you want to wait till the monitorat, also fine, but now we have time. You're busy, you're into it, so please make it now. Do some time management. Take the advantage of doing the exercise now. Okay? If you really do not want to, you just leave it. You do not have to pretend as if you're online, huh? So good friends as well. Huh? I don't. It's up to you to prove it. And so if you want to leave, it's fine. If you want to stay and make it, please do it now, and I'll solve your questions in case you have some. Okay. But we, in a way, treated all the questions of the exam. Huh? You have 3 questions upon the exam. You have a beam type you need to calculate. You have a ship type you need to calculate. And then you have something like this where you have to make the translation to stresses. And that are the 3 exercises you will have upon the exam. Yeah, Antoine, you too. Have a nice day. If you have a question for those remaining and you're making the exercise, do not hesitate to to put on your speaker. Huh? Bye, Jules. You're most welcome to straight put on your speaker. You do not have to ask permission.